Good morning. We discussed last time various formulations of the variation principles, of the least action principle. And it is, well, it may not be obvious at the moment, but it's important to keep in mind different possibilities of writing those variational principles, although they are equivalent mathematically. They may be one of them may be very convenient in one problem, the other in the other. So also equivalent things may have different, it might be easier to generalize one thing than the other. They are not equivalent as far as generalization is concerned. So I would say they may be equivalent in in a plane, so to say, but there is also the axis of generalization, which is anyway. What we said is that we looked, first of all, at reparametrization invariance, time reparametrization invariance, and we managed to write down the action in the form that was then we said, let's play around a little bit and let's rewrite it in the other form. Where h, the function h, is actually an important function. Here, in this particular case, h is, as a function of p and x, is simply p squared divided by 2m plus v. And that's, as we said, it's not accidental at all that we get the total energy here. This is because whatever function, this is a special case. Generally speaking, we can have many different functions of p and x. Whatever you take, it will be different dynamical system, but all of them, for all of them, h will be conserved quantity, will be energy. And the argument is very simple. The argument is that when we take the variation, if we look at we can always set h of t by choosing h of h of t transforms as df dt, h of f of t. And by choosing function f, you can set it to 1. If you set it to 1, you have the action, the Hamilton action. And what it tells us is that if you change parametrization of time, t to f of t, this will not be invariant, but the first term will be invariant, because the first term basically, as I said, it's of course easy to do the calculation. So we write down x of t, x of f of t, and correspondingly for p. But It's obvious by counting dt. You have dt in the denominator here. It cancels this dt, which basically means that you can write it down, this integral, as integral p dx without time at all. So important property of this expression is that when you change f, you get the coefficient according to our rules, we set t plus a of t, and coefficient in front of a dot is just h. This term is not parametrically invariant, of course. Now one more thing. So far it's just a reminder of what I was saying last time, maybe in a slightly different way. We actually can return for a general function h. We can return to the to the x space. So once again, so I'm sorry for being unclear. We extended the number of variables. Now we can say if we originally have been in if we have n particles, its configuration space is just x1, xn, so it has dimension 3n. It's 3n dimensional space, it's configuration space. The phase space, it has double dimension. So dimension of configuration space is 3n, while dimension of the phase space is 6n. It's momenta and coordinate. And it, as I will show you today, it's very useful sometimes to visualize the motion of a complicated system of many particles as a motion of a single particle in the phase space. But returning to what I was saying, we can go back from here to the Euler-Lagrange expression, in which case you have the Lagrange function, and which depends on x and x dot, on coordinate and velocity, and it gives us the Euler-Lagrange equation. So how do we go from here to there? What is the connection? Suppose I want it in this form, although this is usually more convenient and more fundamental. What should I do? Yes. Basically, I can say that let's concentrate on let's call there is a general relation. Indeed, as you said, we have, technically speaking, we vary p. We have the equation x dot equal to dh dp from variation of p. We use this equation to find p as a function of x and x dot, and then we plug it back, and we get some expression which depends on x and x dot, and that this is the Lagrangian. But it would be nice to have it's nice to and useful to formulate it slightly differently, namely the Lagrange function as a function of velocity. I forget about x dependence, which is irrelevant at the moment. You can write it as that it is the maximum value of PV minus h of p. And you maximize it with respect to p. Let's see this has, so this is true for any two functions. They are related by, when you are given the function h, you can, by calculating maximum with respect to p, which is just the same thing, variation with respect to p. You actually actually transform function h of p to the function L of v. And you can, this is, as I said, is called the Legendre transformation. And it actually plays some role in many parts of physics, this Legendre transformation. Important feature of it is that, well, let's first look at what it means geometrically. For how we calculate, we have a straight line here. Let's suppose this is the T space. And we have the function h of p. The function h of p, and this is the line dp. For a given velocity, this line is fixed. Now, what is the and so this is the line. If we call it y equal to dp. This is y is equal to h of p. Now, what is the Lagrange function? Now we define the Lagrange function as a Legendre transformation. What do you think it is geometrically on this picture?
The longest vertical plot.
Exactly. Yeah. We have to move this vertical line and find the place where it is the maximum. So we maximize this thing. And this value is precisely the Lagrange function, L of v. Actually, the Legendre transformation is a, well, we will give you some exercises to see how that the square of Legendre transformation, if you perform it twice, you get identity. And there are many other Legendre transformations. I recommend you, we will not stop on it. It's not important for us as it is, but in Arnold's book, you will find some cute inequalities, features, and so on. So I recommend you to read the corresponding section of Arnold about that. For us, it's just important that the Lagrange function, there is one condition which you immediately see from this and from the picture, that if we want a one-to-one correspondence between Lagrangian and Hamiltonian. So the message to remember is that the Lagrangian and Hamiltonian are related by the Legendre transformation. And if we want it to be one-to-one, we need Hamiltonian to be convex function of momentum. But if in some, I can tell you it's one-to-one, but if in some problem you find that the Hamiltonian is not convex, it's not the end of the world. You still can work with it. Sometimes this convexity breaks down, but typically it is there. Okay, now the motivation, it's not, we're still not reached the most general useful variational principle. There will be some more generalizations. But the motivation for writing it in this form was that the phase space, in this case, each point of the phase space corresponds to a particular classical motion. Classical means satisfying the equations of motion. And we wrote down last time the Hamilton equation, which follow from this expression. And we said that indeed we have, if you fix initial data, then the trajectory develops at least in a small vicinity of initial point. It develops smoothly. That's all you need to fix. And now the interest of this formulation of dynamics is that there are some general features typical for all Hamiltonian systems. Not to say that all fundamental problems of nature are they have Hamiltonian description. But before we go to this, and I will demonstrate the power of this method today, a little later, when we will discuss celestial mechanics a little bit. But at the moment, let's generalize it a little more and see some features of this description of system. First of all, one can ask whether for a general system, it's natural to split the phase space coordinates onto momenta and configuration, onto P and X. Whether the phase space of Px type is the most general useful concept, or instead we can have some more general Hamiltonian systems in which it is simply unnatural and asymmetric to split things onto coordinates and momenta. And turns out, actually, the answer to this question in the 19th century was that all interesting systems have their momenta and their coordinates, and you don't have to go further. But turns out then in the 20th century, when people started examining various spin systems, the motion of helium-3, and many other examples, turns out there are examples in which it is extremely unnatural to introduce momenta and coordinates. You lose the symmetry of the system. I must say about this symmetry is that one of the advantages here in comparison with Lagrange description is that when we discussed, for example, the Netter theorem in the Lagrange formulation, we looked at transformations in coordinate space only. We said that we have certain symmetry like rotation or translation, but all that in coordinate space. When we introduce momenta, we can discuss just as well symmetries which mix momenta and coordinates, and that leads to more symmetry and therefore to more information about dynamical systems. So that's one of the reasons for extension. So let's reformulate this thing. That will be the the last generalization before we apply this to concrete problems. Generalize it so that we still have 2n or 6n dimensional space. Let's call, which is spanned by coordinates, I will call it y alpha. So alpha goes from 1 to 6n. So the same space, and but we now look for the actions, for the most general actions, which is not for which we don't split p and x, moment and coordinates. As I said, there will be physical systems. It's not just ideal generalization, because there are physical systems with these properties. And now I'm going to ask you a question. We have to generalize. We want the action in the phase space. This was the action in the phase space, but not the most general one. I want the action which give me equations of motion such that if I fix initial data, then I fix the trajectory. Okay, like here I have to fix x and p, and then trajectory is fixed. Now I want the most general action with this same property. So s, which the function of which depends on y of t, and we want to generalize it somehow. So we first of all, let's do the easy thing. There should be a Hamiltonian, which simply a function on the phase space. Well, that's easy. We have, so the generalization of this thing is simply to say, okay, p and x, we call it y, it's trivial, and we got this term in the action. I will be now talking about h equals 1 gauge. All right, but what about this term? Which expression would be able to give us the first order equation of motion? What we are looking for, if we want this to be defining the trajectory, we need the first order equation of motion in y. So what would be the most general action which generate the first order equation of motion? Any suggestions? Or in other words, let's try to replace in some way this px dot term. How we? First of all, to simplify things, let me rewrite it. Suppose I always can call p, say, x y1, p y2. So I have here y1, y2, y1 dot term. I change notation. And one thing which we can immediately do is when we have many coordinates, what kind of, well, you see, the reason why we got first order equation of motion is because this expression is linear in time derivative, right? If it was quadratic, for example, we would get the Newton equation, this second order differential. So,
can you write a function f of y alpha dot, and
yes, right. That's the most general thing which we can do. Well, let me just finish this. What you said is absolutely correct. Let me finish this line of argument. Of course, we could write down something like some f alpha beta, y alpha, y beta dot. instead of px dot, where f is some constant matrix. Now, one important feature of this is that this matrix must be what? What kind of obvious constraint on f? Okay, it could be time independent, that's fine, but I'm actually have in mind whether it's, what if it is symmetric matrix? Why it is not good if it is symmetric? It's not good if it is symmetric. It must be antisymmetric. So why is that? What's wrong with this action? It's a total derivative, exactly. That we encountered already when we discussed. And as you said, it's, the most general action which we can write down is the following. And now we will make a certain exercise, which by finding equation of motion, which will be useful in many different problems. So that's the most general Hamiltonian system. By Hamiltonian system, I mean that it satisfies the Hamilton equation. It follows from variational principle, and it also leads to the first order equation of motion containing only first derivatives. By the way, what is the energy of this system? Conserved energy. Suppose we use the Noether theorem for this action to derive conserved energy of this system. You actually can see it very easily. Namely, we reparameterize time and see how the system reacts at this reparameterization.
From the rule of thumb of having dt over dt
Yeah.
canceling out, you can say that f of y alpha dot is parametrically invariant.
Absolutely, yeah. You are absolutely right, and the answer is that the energy is simply this Hamiltonian. This function is the conserved energy. So it is like in the px case, no difference. And let's do a small calculation, which will be useful for us, as I said, in many cases. Let's do the variation of this action. We have a alpha y delta y alpha dot plus d. By the way, I forgot to remind you, or I mentioned it before, that when you have repeated indices, the summation over indices is understood. So it is in fact sum over alpha from 1 to 6n a alpha y alpha dot. Usually it's very convenient. It's usually ascribed to Einstein rules. It's not the greatest Einstein achievement, but it's very convenient. Okay, now we have to vary this thing. We write d beta a alpha y alpha dot minus dh dy. Excuse me. This symbol means just the partial derivative. Sometimes I write it like that, sometimes well, I can just stick to this notation. So we're simply moving in a very straightforward way. The only thing now is to differentiate, is to get rid of delta y dot by integrating by parts. That's always is involved in this thing. And the variation of the action, we will get, we will now use the formula that d dt over alpha. You can write it down as, actually it is convenient to call it beta. Let's see, beta. It of course doesn't matter which name I use for this index, summation, because you sum over it. You sum over beta here. So d dt over alpha is d beta a alpha. Or d dt over a beta, excuse me, is d alpha a beta y alpha dot. Because a beta depends on, it's just chain differentiation. It depends on time only because y depends on time. So finally, we get the following expression. That's a very useful variational formula, which we will use in hydrodynamics and in some other cases, which tells us that the if you introduce the object let's introduce this object, and then the equation, the Hamilton equation, have the following form. It's antisymmetric tensor. It's simply now there is one important analogy to this to this formula, and that's the most general Hamilton equation. And things are actually simpler sometimes when you deal with this general form. It's more symmetric and so on. The F, the antisymmetric tensor F, is called sometimes the symplectic form. It's usually the term used by mathematicians. In particular, in Arnold's book, you will find completely different derivation of those things and different notations, but in fact they are the same. Usually antisymmetric tensor, they play important role, and they sometimes called the differential form. That's the term which is used in Arnold's book. Anyway, let's compare this calculation with the following. Let's return back to the very beginning when we have a particle. I set mass to 1. So this is analogy. And let's assume that the particle is charged and you have electromagnetic and you have magnetic field. So you have a system with magnetic field B. magnetic field is usually expressed in terms of, since the divergence of B is 0, it is expressed in terms of vector potential. What is the expression? Help me out here. How? It's a curl of A. And now a slightly less simple question. How we describe, suppose you have a particle moving in magnetic field. What is the action? It should now contain, this is of course the term describing the free particle. We subtract V if it is just the usual scalar potential. But now we have magnetic field, which is described by, we have vector potential AN. N is 1, 2, 3. How to write down, determine the action which involves this vector potential? We want to figure out how particles move in magnetic field, and for that we need to formulate the action principle.
I think I've seen this before. Is it something like you construct a matrix using the vector potential and your scalar electric potential, and that's your effort alpha beta?
Well, at the end it will be something similar, but at the moment I'm asking a slightly different question. We have to figure out, so this term, as we discussed, is a consequence of Galilean invariance and so on. Now, in what can we add to the action which contains AN and which respects all thinkable symmetries? That is the question. And then we will, as a next step, we will start variation of action and so on, and derive all electrodynamics in this way.
So,
Yes?
when you integrated by parts the previous expression, what did you do with the first term? The beta of y, delta y dot? What's the first term?
It is this term which I integrate by parts.
Yeah.
Okay, okay, good. I shall repeat it because that's important. So I get, here are the steps. Concentrate on this term only. Then we have minus d dt, maybe I was too quick here, d dt a beta of y, delta y beta. Now I use the formula which I erased, that d dt of a beta of y, that a beta of y depends on time only because y depends on time. So that means that you have d alpha a beta y alpha dot. And so as a result, you get, instead of this term, you get minus d alpha a beta y alpha dot delta y beta. And then you combine it with the second term, and then, so that's the calculation I just. I really advise you to go through it yourself and get the result, because it's one of the archetypal calculations in this business. So you have to understand which term comes from where and so on. Okay, returning to my question. We know that that the scalar potential is easy to add to this. We just subtract the potential. But now I want to add the vector potential. What would be the natural object? So it should contain the integral over dt, because we want to have a Lagrange function, or plus for that matter. And of what? It would will be no good to say take some one component, say A3, and integrate it over time. Breaks all symmetries. So tell me about something which doesn't break symmetries. So it should be linear in AN, but simply to add AN is no good. You don't know what N is. So we have to short circuit this index with something. So suggest something. What will be, what we have, what kind of material we have in our hands? What can we, how can we eliminate this hanging index n, which breaks all symmetries? To eliminate the index, you need to make a scalar out of vector. You have to multiply it by some other vector. Which vector? We have a good simple vector in our disposal.
Should we do itself?
Well, if you by itself, you get a quadratic expression, and we believe that if the field is weak, the reaction will be should be of the first order. So we have to multiply it by some other vector, which is, it's a simple question actually. It's x dot. If you multiply by x, it's a vector, all right, but you break translation invariance. If you multiply by x dot, you immediately break Galilean invariance. But that's all right. We don't expect Galilean symmetry in magnetic field. Actually, it's, by the way, it's an interesting side comment that if you have, even if you have a plane, like we do in, say, in studying quantum Hall effect, and we have magnetic field perpendicular to the plane, then you see we have translation symmetry in the plane because magnetic field is perpendicular. We have rotation symmetry, but we do not have Galilean symmetry in this case. All right, but let's now use, this is our variation of principle in electromagnetic field. And now using the calculation we did before, let's see what is the Newton equation of motion. So this term after variation gives us xn double dot. What will be, and variation of this term we already calculated, but you have to figure out how it will look here. Or if you don't figure out, the price for that will be to vary it again. But why suffer when we already varied it? So what do you think will be the right side of this equation, of the Newton equation? Modular signs and coefficients and all that is secondary and trivial, but there is a key non-trivial element in all that. So the thing which you have to look at is that was the variation of A alpha y alpha dot, and variation of this thing. Here we proceed. Here we have again, forget the Hamiltonian and so on. So what is the what we'll have on the right-hand side. We obviously will have, we use this formula for the variation, and the only intellectual effort which is needed now is to replace Greek letters by Latin letters. Are you capable of that?
What do we do with x dot square?
Oh, we varied x dot square. As usually integrated by parts and got x double dot. We got just the Newton term. So this is not a problem. The problem is the second term here with the vector potential. What should it contain? What kind of expression? It's basically, the answer is basically written here. And when we translate it, we get dn am minus dm an xm double dot, or single dot. So we got this equation of motion in magnetic field. How it will look in terms of magnetic, in terms of the magnetic field defined here. We can always yeah, it's basically a cross product B and velocity. And this is what's the name of this force? We have a special force induced by magnetic field on the charged particle. It's the Lorenz force, and thus we derive the Lorenz force. Nothing like that, and we see that it's closely related to this differential form, to this symplectic form, which appeared in the Hamiltonian equations. By the way, one more exercise. When we look at this thing, what is the energy of particle in magnetic field? What will be the conserved energy? Again, look at the variational principle and remember our principles. Yes, the second term will not contribute to the energy because it's parametrically invariant. What does that mean? This is the Lorenz force. Now formulate the same thing in physical terms.
People say a magnetic field too.
Why? You can see it immediately here.
Because the kinetic energy.
No, but why this force doesn't produce work? This is the force which is exerted on a particle. Generally, we used that the force generate work. The Lorenz force doesn't generate work. Why? And you can see it immediately from this expression. It's right. The key point is that it is perpendicular to the direction of motion, and the work produced is, generally speaking, is f dx, or this is the power, the work per unit time. When they are orthogonal, there is no work, and they are orthogonal. And on the other hand, you see that this term is invariant under reparametrization, so everything fits. Okay. Now, so the lesson learned is that this symplectic form is analog of magnetic field. And when we say I shall erase this, I guess. When we look at this, basically you can say that what defines the Hamiltonian system, the basic definition of Hamiltonian system, is you are given the following data. You are given the phase space, even dimensional phase space. You are given Hamiltonian, so even we will phase space. Why we will comment on that momentarily. It's important why we need really even dimension. So far we just said that by analogy with px phase space, but there is more general reason why we need even dimensions. We have Hamiltonian, so this is spanned by y's. Hamiltonian is a function of y, and the symplectic form f of y, which is, and there's an important one, very important point about this symplectic form, that it is expressible in terms of vector potential. Magnetic field is expressible in terms of vector potential, which means that it's not any, you cannot take any antisymmetric tensor. It will not be Hamiltonian system. And Hamiltonian systems, they move in a very specific way. So it's not for, it should satisfy certain relation, that it is the relation of expressibility in terms of A. The question is how to write this relation. Again, we return to something more familiar. When we have magnetostatics in this case, what is the condition under which the magnetic field can be expressed in terms of the vector potential? Yes, right. So we need something. Here we have more dimensions. By the way, this is a completely general equation in any dimensionality, while of course this transition is three-dimensional, specifically three-dimensional. So we need some condition analogous to the condition that divergence is zero, or divergence of magnetic field is zero. And it is easy to find. Actually, these conditions are. Let's first solve a simpler problem. It's again, to understand it, you have to look at the problems of this type. So let's look at the problem. Suppose we have not a tensor, but a vector. And to stress that it's not related to these vectors, I call it C alpha. And you are asking the question, under what conditions C alpha can be expressed as a derivative, as a partial derivative of some scalar. Or in vector notations, when the vector is the gradient of a scalar. What do you think is the answer? When this equation is solvable? Exactly. So you need d alpha c beta minus d beta c alpha to be 0. What is it in terms of vector, familiar vector analysis? Huh?
Circle.
Circle, exactly. Good. Now we are ready to generalize. Now we are asking the similar question, but for the higher rank. We are asking when is some analog of the curve. And you can check, and should check actually, that the answer is very simple for any dimensions. If you take, it's already clear that we need some kind of, we need to differentiate it and antisymmetrize and get some relation. So let's look at the following expression. D alpha f beta gamma plus we will take cyclic permutation. So alpha here was on the first place, we put it to the last place, and so on. So we have d beta f gamma alpha plus d gamma f alpha beta, and it must be equal to 0. Now it's very easy to check that if you have 3 dimensions, that is precisely the condition that curl is 0, as you said. Excuse me, that the divergence, of this thing is 0. It's precisely the divergence of the magnetic field. But it's true for general case. And if you simply plug in this expression, you will see that all derivatives cancel. That's a very simple exercise. That you will have d alpha, d beta, d a gamma, and so on and so forth. Everything will cancel each other. And that is called, what is very cute is that this sequence continues to, it's not related to Hamiltonian system, but it's very important statement that then you can look at the, say, tensor H alpha beta gamma, which is totally antisymmetric, which is equal to, and ask the question when it is expressible in terms of some other tensor f. And once again, you'll find that d alpha h beta gamma delta plus cycles is 0. This statement is called the Poincaré lemma, and actually it is the basis of very important topological notion called cohomology. But I will not go into this, of course, but still it's a nice and clear thing which has purely geometrical interpretation. So far we've been algebraic, but I don't plan to go into topology, but just to mention it, it's the condition that when you have a manifold has a boundary, but the boundary has no boundary. So it's a condition that when you take twice boundary operator, it gives you 0. Anyway, that's all unimportant for us, but worth knowing, worth remembering. Okay. So now we will derive how we're doing with time. Good. We will derive some general properties of Hamiltonian systems. So finally, the definition of Hamiltonian system is that, I forgot to say about even-dimensional. It's even-dimensional phase space, Hamiltonian, symplectic form, which can be any antisymmetric tensor satisfying the condition Actually, it will be some intellectual exercise for you to establish connection between what I said and what is written in Arnold's book. When you look at what's written there, you will not, at first, will not recognize anything. But eventually it is, and actually it will be useful for you to understand mathematical notations as well. It's just a matter of notations. So, we have this Hamiltonian system, and we have the phase space, and we now want some general properties of this motion. And I shall actually begin with something quite simple. Suppose that we have, first of all, let's introduce the notion of the, well, we'll see. Suppose you have some arbitrary function on the phase space. And let's begin with the usual space Px type of phase space. It depends on time, because P and X depend on time. And F dot this expression actually has this antisymmetric expression has a special there is a special notation of it called the Poisson brackets, and although it's called this way, there is nothing fishy about this. It turns out to be a very important notion. Of course, we can write down the more general Poisson brackets in this way. We can. Oh, I wanted to say something and forgot. Before we hold on here. There was one important thing which I forgot to mention, namely, in order to, we can always write down it in the form where E is inverse matrix to F. We just invert this relation. But it immediately tells you that in order to, only then we can say that initial data determine the motion when we can invert it. But in order to be able to invert it, we need the determinant of F non-zero. Now there's it is possible the determinant is non-zero only in the even-dimensional case, even-dimensional space. Because for a simple reason, when you have an antisymmetric matrix, so transpose matrix is minus F, how would you argue that the determinant is in the even-dimensional case must be zero. In the odd-dimensional case, excuse me, the determinant of it's a very simple statement and quite general that when you have antisymmetric matrix, in odd-dimensional space, its determinant is always 0. And so this equation is not invertible. The proof is that you take the determinant of this relation. It's the same as determinant of f, and it's the same as -1 to the number of dimensions. So that's because when you change f to -f, the determinant, even-dimensional determinant, doesn't change sign, while odd-dimensional changes sign. So for any matrix, we have this situation. So that's why the phase space is even-dimensional. And I will need this here. So, and I will need this things here. Of course, we can write it down as the inverse matrix d alpha h. We can now, and this is the general Poisson bracket. There's the Poisson brackets, as we will see in a moment, is very closely related to commutators. It's a classical version of commutators. And there's a curious story which I read, actually. Dirac wrote some memoirs in which he described how he discovered quantum mechanics. He said that he went on Sunday for a long walk, and then suddenly realized that the commutator that he tried to deal with non-commuting variables. Actually, quantum mechanics is the same as classical mechanics, except that the number system is different. The things are non-commutative. He, in a flash, he realized that commutator should be related to Poisson brackets. However, there was a problem. He couldn't remember what the Poisson brackets are. And the library on Sunday was closed, so he described how he spent a very bad night trying to remember what it is and so on. But finally, well, I hope you will know after this course what the Poisson brackets are. So the only thing which remains is to invent quantum mechanics. Well, let's try to understand this connection with commutators. This connection with commutators appears already in the framework of classical mechanics. So let's, and this is very useful. So what I'm going to say is that this definition it's a complicated thing, complicated expression, but it's analogous in quantum mechanics is just HF minus FH, and as such it satisfies the following relation, which is extremely important for the whole Hamiltonian dynamics, that ABC plus B CA plus CAB is 0. This is called the Jacobi identity. And it is You can prove it in a straightforward way using the definition, but it's quite tedious. Actually, it's not that. The algebra is complicated, many terms canceling, and it's not clear. If you replace those definitions by commutators, it's completely obvious relation. You just write down a few terms and you see that everything, say ABC from here will cancel the ABC from here, and completely trivial, no algebra at all, which is one of the demonstration of this thesis that quantum mechanics is simpler. The only thing is to understand in what sense Poisson brackets can be understood as commutators. And for that I need to tell you a few things about commutation and about the meaning of commutators. Well, you see the most obvious example of non-commutativity is just when you take, say, this eraser, you rotate it 90 degrees this way, then 90 degrees this way. When you do it in the opposite order, you will get a different position of the eraser, obviously. How to see this and how to understand this? We will now do this. Again, it's easier to do using algebra than geometry. And after we understand it, we will understand that Poisson brackets are just special case of commutators of certain. Let's remember that we have the variation of x corresponding to rotation. Suppose we look at the infinitesimal rotation. And infinitesimal rotation is given by this formula, or more generally, delta x alpha, where omega is antisymmetric tensor, once again. Okay, now how to check that, how to see from this that the rotations are non-commutative, that rotations don't commute with each other. Well, let's imagine that we have let's take the eraser, which density of which depends on x in some way. This after rotation, this function changes, and we have some. If rotation is infinitesimal, I actually demonstrated to you finite rotations, but it's easier to deal with infinitesimal rotations. So consider infinitesimal rotation, action of infinitesimal rotation on the density of this object. How would you write it down? What is the delta rho induced by infinitesimal rotation? Okay, suppose I do translation. What is delta rho corresponding to translation? That's a trivial question. What?
Are you just translating the exponent?
Yeah, but since I'm considering infinitesimal translation, so for translation I will have A and the gradient of rho. For rotations, so this is translation. For rotations, I will have delta rho omega x ddx rho. Or for, so the, say, for rotations around the axis number 1, I will have x1, x2 d dx3 minus x3 d dx2 applied to ρ. For rotation around axis number 2, I have 1, 2, 3. I will have x3 d dx1 minus x1 d dx3 applied to ρ. And now suppose, so this is rotation around the axis number 1 and the axis number 2. What should I do to calculate the commutator of this rotation? Suggest me some simple procedure to examine. What I want to know is that if I rotate around 1, then around 2, minus vice versa. How to calculate this using this expression? It's straightforward, actually. So what should you do? Yeah.
Multiply the parentheses of 1 and subtract the multiply.
Yep. Yep. So delta 1, 2, or delta 2, 1, if I do it first around 1, 2, I will be x2 d3 minus x3 d2 multiplied by sorry, I think I have this like to ρ, and here I shall write down x3 d1 minus x1 d3 applied to this thing. So these are rotations R1, R2, R1 applied to ρ. And now if I do it in the opposite order, I will get x2 d3 minus x3 d2, x3 d1 minus x1 d3. They don't commute because this guy, this guy is, it doesn't differentiate anything here, so there will be no contribution. But from this guy, you will get non-trivial term which contain x1, d2, and so on. And if you complete the algebra, if you simply simply calculate, you will find that R1, R2 minus R2, R1 is equal to R3. I suggest you do this yourself, since we're out of time. So we see that the rotation is already a classical rotation. We are not introducing quantum mechanics. Is already non-commutative. In quantum mechanics, all variables are non-commutative. In classical, it's only part of it, part of them. Some we still think of coordinates as usual numbers, but transformations can be non-commutative. So in this sense, classical mechanics is eclectic, while quantum is much more beautiful. Well, what I will show you next time is that you still can understand in classical mechanics the Poisson brackets as commutators defined in some way, although they are not as straightforward as in quantum mechanics. Okay, let's stop here.